take a look at this example here, Calc 37.4, applications of derivatives of trig functions. Okay? So this question says this, a beacon, and so when we're talking about a beacon, it's like it's like a light from a lighthouse, you know, the actual sort of light, is located perpendicular distance of 315 meters from point R on a straight shoreline. So let's just draw over here. Let's draw the lighthouse. And here's the light. It is located exactly 315 meters from this point R, and it's on a straight shoreline. Okay? Let's pretend that's a straight line. All right, so just jot down what you see. Now, this is interesting, this piece of information right here. Girls, you all right? Okay, this little piece of information is interesting right here. It revolves at 1 revolution per minute. So when we have revolutions per minute, that's a rate of change, right? It's something per something else. So revolutions, I don't know, you know, revolutions times around a circle. We can't use revolutions as a variable. But what can we use as a variable that we have been using in questions like this? What is 1 revolution? Circumference. No, the circumference would be the perimeter of a circle. So think about, not radius, not diameter, not circumference. You're getting close. If this is the center, which it's not, we're talking about what? 1 revolution is what?
2 pi.
Now think about angles, right? Yeah. 360 degrees or 2 pi radians. So we're dealing with radians a lot in math. So theta is going to be, the change in angle is going to be, 2 pi. Actually, the change is going to be 1 full revolution, 2 pi radians per minute. How do you know that? Okay, well, I can explain it again. Do you want me to say that again? When we're talking about revolutions, we're talking about it rotating around a circle. Okay, so not circumference, because we have nothing to do with the radius of anything. We have 315, but we're not actually measuring this part of a light path or anything, right? So that's out. Not the radius per se, because radius is a number that's given, and the radius isn't necessarily changing. I mean, you know, the light shining is getting longer. It's a little bit different, but we're not talking about, you know, concentric circles, right? Like this. This isn't really making sense. So it's not radius. So how does that revolution, that sweeping, that revolving, in these types of questions, at 1 revolution, think about the angle that is passing, the angle that is represents that revolution. So it would be 1 time around would be 2 pi radians, and if it says 1 revolution per minute, that's our rate of change of this angle. Okay, does that help? All right. So the rate of change of okay, good. That's a good question. Okay, how fast does its beam sweep along the shoreline? So the beam of this light, how fast does it sweep along the shoreline? Now what you have to understand here is that as this beacon rotates, the beam of light is rotating, and it is starting to, like, it is sweeping along the shoreline, right? And it's actually getting quite a bit faster as the beacon turns. You see how it is? It kind of like it moves this rate here, from here to here, then from there to there, and then a bigger jump, bigger. You see that? So it's actually changing speeds in reference to the shoreline. So that's interesting. But what we're talking about is, what is the rate of change of this distance right here? What's the rate of change? The derivative of, let's say this length would be x. At the point S, let's say this is S right here, that is 425 meters from R. So this is going to be at x equals 4.25. Okay, so we're asking for the rate of change of x. This is the movement of the the light along the shoreline when the light is exactly at the point 425 from R. So what instant in time are we talking about? We're talking about that instant in time when the light is shining 425 meters from the shore, from R. Yay, nay? Questions so far? That's why I know this is a tricky problem, so that's why we're going over this. Once again, just take a minute to clarify again. We have a beacon that is situated 315 meters, so that's not going to change. This distance is not going to change, right? The lighthouse, or this beacon, is this far from the shore. It's not moving. What is moving, though, is the rotating of the light. That's moving, so we've got a rate attached to that. That's 1 revolution per minute, or 2 pi radians. Because remember, revolutions, that's not a variable, but angle is, so 2 pi radians per minute. That's our first rate of change. How fast does its beam sweep along the shoreline? And again, that is the light beam sweeping along the shoreline. Okay? So it comes like this, and it starts to increase fast, and then it spins all the way around, and then comes fast in here, slows down, and then speeds up. Right? Fast, slow, slow, fast, right? Yes, I'm saying that each of the difference between each of these blue lines would be the same angles. Yeah, the same little bit of change of direction. Yes, but what's happening is, because this shoreline, right, is straight here, this line, actually the length of this line gets longer, and the distance between each successive point of impact here gets wider as well. Okay, so we got 2 related rates right here. One's given, one's unknown, and we've got some instant in the question that we are going to focus on, and that's when this distance from R to S is 425. Okay, so far we're pretty similar to, well, I don't know if we're similar, but it's kind of like the last question that we just worked through. But all right, so let's keep going here. How am I going to relate now theta, right, this theta here, and x, because theta and x are my 2 rates. So is there an equation that I can write that relates x and theta? And if you think about this triangle, that I'm really messing up here, but if you think about this triangle, that is a right triangle, then you should think, oh, trig functions. Yeah. So how is x and theta related if we consider this 15 that's given? Opposite, adjacent, right? Okay. So if x is opposite and 315 is adjacent, that's TOA, right? Opposite over adjacent. Then we're using the tan function of theta. Everyone see that? Okay, so here's an angle. Opposite, adjacent. This would be the hypotenuse, wouldn't it? Okay, that's the hypotenuse. So opposite and adjacent. These 3 quantities are related by the tangent function. So, ka, toa, right? Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tan, opposite over adjacent. Yes? No? Good? Okay. So then what is x? Again, you could go right from here if you want. Usually, division, quotient rule, you don't want to do quotient rule if you don't have to. X equals 315 times tan theta. Question? Good. What are you guys talking about? You're good now? Okay. So here's our relationship now. Now we take the derivative, right? With respect to time, take the derivative, and I've got x prime equals 315. What's the derivative of tan? No, secant squared theta? Probably. Okay. And then am I done? No. Chain rule. Okay. Because theta... What? What did I say? Chain rule? Jane rule? Did I say Jane rule? Okay. Okay. So, again, just like the last question that we did, this, are we given it or do we need to know it? We don't know it, so we're trying to find this. Okay, this one we're given, right? That is given to be 2 pi. And this, are we given this? Nope. So we're going to have to try and find it. And again, this applies at the instant that we're concerned with here in the question. So you've got this triangle again, and x is, at this instant, it's actually 425, right? So you now can see there's a relationship. This is 315. This is 425. And this is a right triangle. So now you can set up an equation to find out what theta equals. And we have tan theta equals 425 over 315, right? Set over adjacent. Make sure that you're in radians here in your calculator if you're going to find this theta, because obviously theta here is in 2 pi radians. So if you're going to be looking for a theta in this question, it's got to be radians, not degrees. So, okay, so I'm going to hit that. And so we go, what? Second function tan of, I did that calculation already. Answer 0.932966. If you can use exact values, do that. Not necessarily can you do that for each question. This 425 over 315, or that's not on the unit circle, so I wouldn't worry too much about that. Just use decimal then. So this is what we have then. We have x prime is our unknown equals 315 times secant squared of times 2 pi. And so once you evaluate that all out, then that should be your x prime. So go ahead and take a minute just to do that, see if we get the same answer in the end here. All right, so just in decimal form, here's your answer. So you finish that off with a little sentence saying the beam is sweeping along the shore at approximately 5,582 meters per minute. Okay, so here's your answer for how fast the light is sweeping along the shore. Okay. Any questions?